breaking the rules. It says no drinks. Yes, I am. Am I on? Can you hear me in the back? No? How about now? That's good? All right. Thanks, everyone, for joining me this morning. I am Spencer McIntyre, and we're going to talk about Metasploit and some Windows kernel exploitation. Fantastic topic. So thanks, everyone. So this is a real quick agenda of what we're going to go over. We are at the agenda phase, of course. We're going to talk about kernel exploitation overview and basics, so sort of define some terminology, take a look at a little bit of the history, and see about where we've gotten up to here. And then we're going to start to get into the Metasploit specifics, how Windows kernel exploits are often being implemented in Metasploit, some of the common tips, tricks, and techniques that are being used through those. You not here? Is that better? Yeah? Okay. Yeah, so we're going to talk about the... One sec. Okay. Stand by.
Ladies and gentlemen, good morning. It's my great pleasure to introduce to you Mr. Spencer McKay.
McIntyre. That's okay. Agenda. All right. Yes, so we're going to go over kernel exploitation overview and basics, talk about some of the things that have gotten up until now. So nothing too Metasploit specific in that section. But later on, we're going to talk about what common techniques and tricks are actually being used in Metasploit, how the exploits are being laid out, things like that. And then finally, we're going to talk about improving reliability of exploits. I want to say, so I wanted to submit this presentation because kernel exploitation has been something I've been really interested in for a while, and there's a lot of fantastic research out there. There's a lot of research out there, though, that is ranging from highly theoretical, super cutting-edge stuff to things that are very practical. And so kind of what I wanted to do was I wanted to sort of bridge the gap and show like some of the more cutting-edge, practical techniques and how they can actually be used in exploitation from a pen tester's perspective. Because pen testers often have a very different perspective than, say, security researchers that just needed to work one time perfectly, whereas pen testers have a much higher emphasis on reliability. They need something that's going to be more reliable, not be a saw at the box and lose their session. So it's a little bit of a different angle, so that's kind of what I want to take today. But before that, about me, as mentioned, I am Spencer McIntyre. I work at SecureState. I have the privilege to do research development and special projects there, which is a fantastic thing. I'd like to think I am a BSides inducer, at least while doing the research for this talk. I've done many a blue screen, but you learn to love it. I'm an avid open source contributor. Metasploit is probably the project I contribute to the most. Huge Python enthusiast, so really like Python. And I've got a couple of certs after my name. So BSides warning. Any of the techniques that we're going to talk about in here, whether you're doing it right or doing it wrong, you are eventually going to have a blue screen. So I do try to propose a lot of solutions to different problems that I'll discuss throughout the talk, and no one solution is going to work for all or maybe even like half the problems. It's kind of like we always tell people in security that there's never that one silver bullet that fixes everything. Well, it's kind of the same from this perspective on the offensive side, that there is no one solution that's going to be applicable for every vulnerability because they are all unique. That's why they're vulnerabilities. So they're all unique and need to be a little bit more specialized when actually working with them, so whatever's going to fit the situation. So with that, we're going to jump right into kernel exploitation basics. So why kernel exploitation? Why do we care? It's been a growing trend that remote code execution vulnerabilities just haven't been coming out like they used to. A long time ago, they might have been coming out a little bit more frequently than they do now. Arguably, the last greatest remote code execution vulnerability that was in like Microsoft Windows was MS08067. So over the past couple of years, I've heard people talking about it less and less about how they occasionally might find it on a Windows system on a pen test. Maybe nowadays, if they do, it's definitely that old dusty box in the corner that nobody ever really talks about. But the point is that remote code execution vulnerabilities, they're not popping up as frequently. And when they are, they're showing up in more third-party software, so things that aren't actually being developed by Microsoft specifically. And so that leads us to why do we need kernel exploits? And that's because like sort of the attack landscape is shifting to doing more client-side exploitation. That would be things like browser-side exploits, or what is more commonly probably social engineering. Because once again, from a pen tester's perspective, all the pen testers I know, none of them are really going to jump right in and be like, yeah, I'm going to use that latest IE 0-day. Because it's not going to be as reliable. The users might be running Firefox or Chrome or something. It's just not going to be as reliable as a social engineering. But regardless, when using a client-side exploit, when it is successful, you get the privileges of the client. That's not full system level access, and that's not going to be enough. I know that's not enough for me. I always want to completely own the box. I want that system level access, and so oftentimes kernel exploits are the way to do that. And the reason why they are a fantastic way to do that is because the kernel is always going to be there. If you turn Windows on, the kernel is there. There is no way around it. It is always there. It's not a service that needs to be turned on or enabled. Win32ksys is always going to be loaded when there's a graphical environment. So all those client systems, all those servers, they all have. The only way you can get around not having the Windows kernel there is using Linux or OS X, using something that's not Windows. It is the heart of Windows. So. And then finally, where are the vulnerabilities coming from nowadays? Some of the great sources of where the vulnerabilities are coming from is there's a fantastic competition, Pwn to Own, hosted by ZEI at CanSec West. And after the competitors have finished their competition and walked away with their small mountains of cash, they often post fantastic, highly technical details about the vulnerabilities that they use. Not all the time do they release a public exploit, but they at least talk about in great depth some of the vulnerabilities that are out there. In addition, there's some fantastic details and work being released by companies that are finding these exploits in the wild. Companies like FireEye and Trend Micro both have recently posted very highly detailed blogs about zero-day kernel exploits that they're seeing in the wild. And so people have been able to use that research and actually build up exploits from what those disclosures were talking about in the vulnerabilities. So earlier this week, I went through and I made a list of vulnerabilities, of recent vulnerabilities that I thought were notable for one reason or another. I ended up going through these thinking that maybe not all of them would actually have a public exploit code, but I marked these ones down as notable because there were some additional technical details that were released beyond just the standard Microsoft Advisory or the CVE. Excuse me. If you've ever seen a Microsoft Advisory, there are no good details in it. It basically says, hey, there's a problem. Somebody might own your system if they have local access. That's it. There's no technical details. They don't tell you the function or what type of vulnerability it is. There's nothing good in there, so it's not particularly interesting to me. But all of these vulnerabilities, there was some type of additional research done that somebody was able to release a blog, a white paper, something like that, actually detailing in great depth the nature of the vulnerability, and that ultimately ended up leading to exploit code. The one that I want to point out that has DOS next to it, MS-1534, that was a very interesting vulnerability. That is the only one on this list that is not actually a local kernel exploit. That is a remote kernel vulnerability that was triggered in one of the drivers used by IIS. So that wasn't very unique in the fact that an attacker could trigger that remotely and cause a kernel pan, but still very interesting. So I want to talk about some of the common vulnerability classes. So what are the types of classes of vulnerabilities? Because a lot of times when people think about exploitation, they're always like, oh, you know, the stack buffer overflow. Or maybe if they know a little bit more, they might be talking about like keep corruption or use after free or something like that. But in the kernel, it's a bit different. Stack buffer overflow I have mentioned as like an honorable mention because it's not as prevalent in kernel space. There's not as many exploits that are coming out that are exploiting a stack buffer overflow in the Windows kernel. I actually can't think of an instance where I've seen a recent vulnerability that has been in that case. Pretty much these top three categories of like a write while where, a null pointer dereference, or use after free, those are really the main three categories that these exploits are coming out as, or the classifications of these vulnerabilities. So write while where. So this is basically when the attacker can control data and they can control where it is written. Ideally, if they can have full control over the what and full control over the where, kernel exploitation is relatively trivial. This is one of the oldest vulnerabilities that I've been able to find in some of the kernel exploit realm, and is often very stable, which is one of the benefits about it. Because there are very, very well-documented techniques that you can use this to gain code execution reliably. And it can be triggered multiple times on demand. We'll get into that just a little bit later. But these are often found in also in third-party drivers. So these are often also found in drivers that are not necessarily developed by Microsoft Windows. But there's been a couple of instances where antivirus vendors have had drivers that have been vulnerable to this, or other types of drivers. And the vulnerability is often triggered using an IOCTL to NT-device IO control routine. And usually the exploit consists of something about setting up a buffer in a specific way in order to trigger a vulnerability, and then sending in the specific IOCTL to trigger the vulnerable routine with the malformed buffer. And that ends up writing attacker-controlled data to an attacker-controlled location. Not all the time is the attacker able to control both, but if they at least know what is being written and they can control the where, controlling the where is more important than being able to control the what oftentimes. And then a couple of examples, ranging from 2011, there was MS1180 that was released by the offensive security guys. They did some fantastic research on that, and then ultimately ended up releasing a Python exploit for that. And then more recently, and I think it was like the third or fourth quarter of last year, MS1470 was released. And both of these were using that anti-device IO control file to trigger a write while where condition with a malformed buffer. So, pretty interesting. A null pointer dereference. So this is what occurs when an object is being referred to at an address of null. Not always at an address of null, though. There's been a couple of instances where a negative number or a very high number has actually been referred to as an object, but because the very low part of the object that would be in that super high address range is not actually being referenced, it's not an exception until it reads something later on in the object. The object is 300 bytes, and negative 16 is being referred to as the number. Then as long as those first 16 bytes aren't being referenced and something at like an offset of, say, 60 or 80 is being referenced in the object, then it's still going to be at a very low address. That's something that the attacker can control, and that's the most important thing. Exploitation is often more stable in this case than use after free. In my experience, between the use after free null pointer dereference and the write while where, this one's somewhere sort of in the middle. And the reason, there's two reasons primarily. Number one is that an attacker can often determine whether or not they are able to allocate the null page before they end up corrupting critical structures. So they can tell with a good level of certainty this exploit will most likely succeed prior to corrupting anything, so before they hit that point of no return. Secondly, the attacker only has to have a freed object, and they often, if the address is at a lower address, they have complete control over being able to corrupt the object, which is very beneficial for them because they have that great deal of control, which is not always the case, or is very rarely the case with the use after free. And like I mentioned, there's another thing. When dealing with 64-bit environments, it's often also beneficial to look for pointer truncation. When MS1458 came out on the Windows system, the negative number that was being returned from an error code that was then being used to reference an object was being truncated to 32 bits on 32-bit systems. So on a 32-bit system, that was like the whole pointer space, so the attacker had to map out the null page. But on a 64-bit system, because that was being truncated, it was actually easier for the attacker because they didn't really have to mess with mapping that null page because it was at a much higher address. So they're still able to get that. So of course, that's going to be very vulnerability dependent, but this is something to watch out for, something to keep in mind. If you're looking at a 32-bit vulnerability, try to trigger it on a 64-bit system and see, maybe you'll get lucky. I tried that another time, and it didn't quite work out. The pointer wasn't truncated, so it wasn't quite going to work. Next up, we have use after free. So use after free is, of course, going to occur when a pointer to an object is used after it has been freed. And the problem here is that if an attacker can reallocate another object in the space after that object has been freed and before it's referenced again, then they can potentially manipulate the reference of that afterwards and have it do malicious things. And the reason why this is probably one of the least reliable ones is that after an attacker has freed that and started to reallocate objects over there, they've kind of hit that point of no return, and so it's a bit more difficult to determine whether or not the exploit is going to be successful prior to corrupting potentially critical structures. So it all depends on what is actually being corrupted, but in general, it's a little bit more difficult for them to determine that. Additionally, an attacker has to be able to find out what object they can actually reallocate at the same space. So they need to be able to find a suitable object to do that, and that's, of course, going to take a lot of time and a lot of effort, but we'll talk about that in this minute in the code execution step. Last up, example of this one's very recent one, actually the most recent one, was the MS1520 vulnerability that recently came out. That was the 1-bit to rule them all. There was a blog released by... in my references, I can't remember the company, but it was a fantastic research blog that was posting out how they were able to allocate a different object over the one that had been freed. So now that we talked about vulnerabilities and we kind of know what types of problems do occur, that's not enough for us. That might trigger a blue screen of death, but that's not good enough for us because we need to be able to do something useful. For a local privilege escalation vulnerability, a blue screen is worthless. That's going to kill your access. That is a step backwards. So there's no room for error in this. It's not like a remote exploit where you might just want to DOS the box out of spite, like that's not useful to an attacker at all. We need to be able to have reliable code execution. And the way that we get to reliable code execution depends largely upon the vulnerability class. Like I mentioned, the write what where is a very well documented technique. A lot of exploits use a write what where vulnerability to overwrite a critical pointer in the how dispatch table of the kernel. This how dispatch table has a callback function that is within it. And what makes it very suitable for use by attackers is that after that pointer has been overwritten, the attacker can trigger their shellcode execution on demand, essentially, by using an additional function called ntquery interval profile. They can call this function, and then that pointer that was in the how dispatch table will be called on demand by the attacker. And it ends up being very reliable code execution. And what's also very nice about this is that the attacker often writes their shellcode into userland. That's usually where it's stored in general. And so after the attacker has run their shellcode the first time, they've elevated themselves to the system, they've done what they needed to do. Hypothetically, if they need to run code within the context of the kernel a second time, they don't necessarily need to re-trigger the write what where condition. They can just replace their shellcode in the same position and call ntquery interval profile a second time to execute a different set of shellcode if they needed to do something like cleanup operations or anything like that to restore the token. So that can be a very reliable technique to use. Okay, and then null pointer to reference and use after free, they are similar in the sense that they are highly dependent on whatever object is being corrupted. In the case of a null pointer to reference, it's if an attacker can map that null page, if that is possible, the attacker has full control to be able to corrupt that object. It's much easier for them because there's nothing really blocking them from manipulating and setting up the object exactly as they want. A use after free is a bit more difficult, though, because the object is oftentimes not in the userland space. The attacker needs to find an indirect way to be able to create an object that is going to be in a suitable location to replace the one that had been freed, and then find a way to be able to write those fields and corrupt that object in such a way that when they're done corrupting it, it's then usable to them for some type of code execution via whether they're going to trigger a write what where condition or a call or something of that nature. So once that object has been corrupted, they need to be able to get that into a primitive. Sometimes they'll then use this to be able to achieve like a write what where condition. All of this is very highly dependent on whatever object is created. So what's going to go into that is going to be a few different factors. Size definitely affects it, the layout, and the destination heap. The Windows kernel does manage multiple heaps, just like the desktop heap and the session heap, and different objects are created on different ones for different purposes. So you need to have an object that's going to be allocated on the same heap, otherwise it's never going to be allocated over the space of the original object that had been freed. All right, so a very useful object is going to be the window object itself. The reason why I wanted to point this out as a very useful object is because it can be used to reliably trigger code execution if the entire, or not necessarily the entire window object can be corrupted, but if two specific parts of the window can be set. The window object does include a callback function in the LPFN winproc procedure, and that can be set by a user. But almost all the time, most of the time, this is called within the context of the user process. So the kernel switches context back into the user and then executes this callback procedure. That can be manipulated, however, if the attacker is able to set the B server-side window proc flag. If an attacker can set that single bit in the window structure, they can then reliably trigger the execution of the callback on demand, and from there they'll have kernel code execution within the context. And they can use that to then elevate themselves to system, clear out ACL, or do whatever they need to do, but they'll have full, complete privileges, even arguably beyond system-level privileges. They'd be executing within the kernel from that point. So that can also be a bit more reliable if you can reliably corrupt the object. Okay, so we're going to talk about mitigation technologies a little bit. Mitigation technologies are something that has to be dealt with now. XP is dead. It's gone. Like I mentioned, the only ones that are still sticking around are probably the old dusty boxes back in the corners. And with XP died the days of jump ESP. It's just not enough anymore. Nobody's really executing code off of the stack for a real production exploit if they're not just learning. So a couple of the common mitigations that I want to talk about is going to be like ASLR. It's going to be address space layout randomization. For a local privilege escalation, it's only kind of an issue. And I say it's only kind of an issue because if you already have code execution up to the point prior to triggering your vulnerability, you can actually resolve all the addresses in user land without a problem. So all the addresses in user land you can resolve pretty easily because you have full access to read all of that memory. You can do version detection. You can use fantastic functions that Microsoft has made available, like load library and get proc address. You can use those to resolve those addresses dynamically, and you can get around ASLR by that. So the only thing you really need to worry about are those addresses in the kernel land, because you still can't read those for the most part. However, you can find the base address of drivers. You can enumerate out and find what drivers are available, and you can find like the base address of the kernel and the base address of like Win32k sys, and you can find those. And so from that point, you could use a static offset or something of that nature. Additional structures that are allocated by the kernel beyond just those, if you do need to be able to read those, you're going to have some type of like a read primitive, which would be dependent on the vulnerability. But that's going to introduce a great deal of complexity into the vulnerability if you're trying to use that to read data out and then make decisions based on that. And then data execution prevention. Strictly speaking, data execution prevention is not necessarily an issue in versions prior to Windows 8 because you're going to have things like NT-allocate virtual memory and virtual protect. Where because you have code execution ahead of time, you can just set the read, write, execute permissions on your shellcode yourself. So you're not going to trigger those DEP preventions. Something that is a little bit similar, though, to DEP is going to be SMIP, which we'll talk about in a second. Another mitigation technology that is very effective and has actually been around for a really long time is null page mapping. So basically what happens is that the process that wants to protect itself from being utilized to map the null page and then trigger like a null page dereference can map the null page ahead of time. It can map address 0 with page no access and essentially just squat on it. Like people just like buy domains and then just like squat on them. They can basically do that, and they can allocate that page and then just squat on it, and then for the remainder of the life of that process, nobody can access that page. You can't read from it, you can't write to it, you can't reallocate it or anything like that. So this is actually one of the oldest protections in Emmet. This is actually how Emmet does provide the null page protections. And some of the newer versions of Windows, they prevent you from allocating the null page. So it depends on how you're actually going about it. But for the most part, this is the protection. This is how people protect themselves. Even without Emmet, though, processes can still map the null page manually. They can essentially implement this protection relatively easily by just implementing that call and squatting on the page so nobody else can use it. But from our perspective as an attacker, it's not really an issue because by default, processes are not generally mapping the null page and squatting on it. So from a pen tester's perspective, if you have an interpreter session and you want to escalate yourself with a null pointer vulnerability to get that system level access, and the process that you're currently in is squatting on that page, you can oftentimes either spawn a new process or migrate over into one that's essentially not being protected. So it's basically up to the attacker to try to get out. So unless you're sandboxing, you can't do that. It's not particularly an issue. So something else that is an issue, though, is going to be supervised remote execution prevention, which is SMIP. SMIP was developed by Intel a while ago, and then Windows 8 recently implemented support for it. So it was in the actual Intel specification prior to being supported by Windows. But when Windows 8 came out, they did add support into it. And so in this case right here, this is the new Windows 8 style blue screen. And right down there at the very bottom, we see in all caps, it's tempted to execute a non-execute memory. So this is actually the exception that would occur from SMIP. So at this point, I was trying to, with MS 1440, I believe, was trying to execute shellcode in user land from the context of the kernel. So I just switched it back just like it was Windows 7. My mistake, I got a blue screen. But this as well, never fear, there is a very well documented technique for this as well that you can use to disable SMIP. There's a blog also in my references by a user known as Juru, who basically did some research on it actually prior to it being implemented in Windows 8, I believe, talked about the Intel specification, why it was created, a little bit about the history of it. But ultimately he gets down into how to get around it, and SMIP is enabled by a flag that is set in the CR4 register. And what he found was that there is a gadget that is suitable for use within ROP, within the kernel, that can be used to disable that value by setting that in CR4. So it can clear that value out. So a couple of the drawbacks to this is that ROP gadget that is a ROP gadget. It's a specific address. It's not a full function, so we can't resolve the address to it like we could for like NT-how dispatch, which is a symbol that we can resolve the address to. Additionally, if you are in a WoW64 process, you don't have the ability to load the kernel and find it, because you can't load a 64-bit executable into a 32-bit process. You can't do that. So if you are in a WoW64 environment, which is probably going to be like the most difficult scenario, because there's a lot of things that get switched around, is that you really have to rely upon a static offset. You have to know if you can somehow resolve the address to the kernel via some like read primitive, you have to rely on a static offset, which is not going to be as reliable from a pen tester's perspective, because your static offset is going to change with patch levels, and what works on one very specific version of Windows is probably not going to work next patch Tuesday. May or may not, but probably not. But what you can do, if you are in a full native process, either 32-bit or 64-bit, what you can do is you can actually load the kernel into your own process space, and you can walk that executable, finding the page LK section, I believe it is, yes. And you can search that memory for the suitable ROP gadget, and then you can calculate out its address from there. And so from there, you have the address in kernel land of where that ROP gadget is, and then when you go in to trigger your vulnerability, you can return to that address, which will clear out that register for you prior to jumping into your userland shellcode that will elevate you to system or whatnot, do what you need to do. All right, so now we're going to talk about kernel exploits and Metasploit. Now that we have all the basics. A lot of the basics. All right, so I like to think of the exploits for the local kernel exploits in Metasploit are primarily divided into two categories based on how they are implemented. They are either implemented all in Ruby, or they are implemented in C and written in such a way that they can be compiled into a reflectively loadable DLL, which is also how interpreter extensions are done. Those are all reflectively loadable DLLs that can get loaded into the process at runtime. They don't have to be local privilege escalation vulnerabilities. There are some Windows kernel exploits in Metasploit that are not local privilege escalations. The IIS vulnerability, MS1534, I believe it was, is implemented as a denial of service. Still technically triggers a vulnerability in the kernel, but we're going to focus primarily on the local escalation bugs that are inside there. So something else that I want to mention, all of them except for one that I found. I was looking at it earlier this week. All of them steal the system token. A single vulnerability, MS1353, which was also a bug that came out of the Pwn2Own competition, they developed a alternative technique to elevate themselves to system by, instead of stealing the system token, they cleared out the ACL of a process that was already running as system. I believe the one that they targeted was WinLogin. Kind of an interesting approach because they're not stealing the token, so they're not going to change the reference count or anything like that. We'll talk about why that's a problem in a little bit. But in the footnotes of the exploit itself, it does actually still mention that when you leave or if you do something that causes WinLogin to die, you might end up running into stability issues. So still might not be the best scenario for everyone. Something to take into consideration. And there's the fancy mix-in. Specifically for Windows kernel exploits. This mix-in provides useful feature functions to be able to resolve the address of the NT-how dispatch table, find driver bases, things like that. So it's right in there. It's in there for convenience so that you can implement these. And then first up, we're going to talk about Ruby implementation. So I want to start out by saying this is probably what some of the older exploits are written in, but this might eventually be deprecated in favor of the reflective DLL style. So it does still exist. I believe they're still accepting pull requests for it, but eventually they might all get ported over for reasons I will talk about on the next slide. But one of the nice things about the Ruby style is that it is all self-contained within a single file. So it's very well suited for things that do not need to make a lot of WinAPI calls. So if you are just triggering a write-what-where condition using like NT-device IO control file, this is a very useful format for your exploit because you can do it all right there. You don't have to worry about writing code in C, loading reflective DLL, or anything like that. So it's a little bit easier if you're just looking for something to get started. The primary flaw with this and the primary downside is that all these exploits that are using this Ruby method are all elevating themselves. The exploit process and the elevation process takes place in the interpreter session that you are running in. So if it fails and it blue screens, you lose your session. But if it fails and the process just dies, you still lose your session. So there's not really any way around that. And failing without a blue screen is kind of what we're going to be focusing on, because if it blue screens, you're always going to lose your session. There's no way around that. unless you have persistence, but that's a little bit outside the scope. But so that kind of brings us up to the C implementation. The C implementation, if you write your exploits in C, it's a lot more flexible. You can use things like threads. If some type of, I've seen situations where triggering a vulnerability blocks something, so you have to, if you need to be able to do something concurrently, you need to be able to use like another thread. It can also be faster to write if you're using a lot of Windows API calls. If you need to like set up a window and format the structure and everything like that, Ruby's not really well suited for creating a structure that you can then like drop into memory, whereas C is very good at that. That's what C is for. Another benefit is that proof of concept exploits can be developed as like standalone executables. So you can debug it, make sure everything's good and working properly, and then format it or switch it over relatively easily to a DLL. So you don't have to deal with like firing up a session every time. So it's a little bit faster for testing and things like that. But the primary benefit, what we really like about reflective DLLs, is that they can be injected into a dummy process, a process that we don't particularly care about. And so what ends up happening is that when you type exploit on your Windows exploit, and what it's going to do is it's going to create a new process, Notepad or Calc or something like that, and it is then going to elevate that process. And the benefit of this is that if the DLL runs into a problem and crashes without inducing a blue screen, you still have your session, which is very beneficial. So that can still be a little bit of a problem when you're in a sandboxed environment. If you have a super awesome IE 0 day and you exploit that and you're still in a sandboxed environment, you might have problems starting up new processes, but that's no matter. These exploits will usually tell that they aren't able to start a new process, and they'll fail over to loading that DLL into the current process. So they'll still do a best effort to try to elevate yourself that way. But generally, we're not running in sandboxed environments, so we can't start a new dummy process and elevate that one. And if that one dies, we still have our sessions, no harm, no foul. So this is the newer stuff. So there's been a lot of exploits that have been coming out, and they all follow this basic format of like these 4 steps. Start out with doing some type of environment detection. Is our session a Meterpreter session? Because I guess some people still use shell sessions, but we just want to make sure it's a Meterpreter session because we need all of that, the power of that API to be able to load the DLL and everything. We also generally want to check and see, are we already running as system? Exploiting the kernel is a very risky business by nature, because if there is a flaw, you are going to lose the entire system, and people generally frown upon that. So if we're already running as system, we're just going to fail gracefully and say, you're already elevated, so there's not really anything that you want to do, really. Next up, after they've gone through the environment detection, they want to do a check to see if they think the exploit is actually going to work. So now this is often what happens when you run check at the Metasploit prompt. That runs some logic, and for most of the Windows kernel exploits, what it does is it finds the driver, the Win32k.sys file usually, and it pulls out the version information from that, and it can determine based on that down to the patch level to see this exploit is most likely going to work against this because this is an older version of the driver. In addition, it's also going to do things like checking to see if any necessary services are up and running. If it needs to open a handle to a specific file or something like that, then it's going to make sure that that's all available as well in the check method. And so that check method will return back and say it's not good, the exploit's probably not going to work, or it'll say you're good to go, the system looks vulnerable, in which case the exploit will use that information to continue on, which is relatively nice. After that, it's going to start up that dummy process, like I'd mentioned. It's going to start up notepad.dll, or excuse me, notepad.exe or calc.exe, and it's going to inject the DLL into that process and elevate that one. That one's sort of the dummy process that if it crashes, we don't really care. But if it is in a sandbox environment and you can't start that other process, it's just going to fall back to loading it in itself and try to elevate itself. And at that point, if the DLL fails, you'll lose your session, which is no good. But at that point, that DLL is going to be loaded in, and it's going to be running that native C code. And from there, it's up to what was already implemented within the exploit to elevate yourself. And hopefully, you'll get a new privileged session as system. So once you do that, and once you actually do have code execution in the context of the kernel, what do you do with it? Well, like any vulnerability, or any exploit rather, you have shellcode that does something useful to you. Like I mentioned, all the exploits that I found, except for the one, they all elevate themselves using the system token. So there's a couple of different ways that the exploits are using their shellcode. A lot of the Ruby ones, all of the Ruby ones actually use a raw string. It's just the compiled or the bytecode of the assembly that's just going to elevate the token. So that's very well suited for the Ruby exploits because, of course, you can't compile anything in C from the Ruby environment. But the C implementations have a bit more flexibility. They can either use that static assembly string of the bytecode, or they can actually implement a function, which is what some of the newer exploits have been doing. So the reason why they've been doing is that the drawback to using a raw string that just has your bytecode in it is that different versions of Windows have the token is stored at a different offset within the process structure. So you need to know what version of Windows you're running against, and so your shellcode needs to be formatted to that. So while it's practical and a lot of the Ruby exploits do that version detection and they patch the raw shellcode in, you do have to do that, so that is a little bit of a downside. And if you don't already have a target for that for whatever reason, it's not going to work. But on the flip side, if you're doing it in C, what we've seen is actually a shift to people that are actually writing their shellcode in C. And the first exploit that used this, I believe, was the exploit that came out about third quarter of last year, which was MS1458. And that employed a very interesting technique that resolved out the PS lookup process by ID function, and then it just implemented a simple find and replace. So prior to the shellcode running, when the code is still running in userland, it resolves the address to that function, and it also tells it, this is the PID that I want you to copy from, this is the PID that I want you to copy to. The copy from PID is almost always PID number 4, because on Windows systems, that's going to be the system level process. So you could use any PID that has a system token, but it doesn't really matter, and 4 is always going to be there, so that's generally what we see. And then that PID that you're copying to is, of course, going to be the process you want to elevate. So this approach of being able to do that find and replace can be a lot more dynamic, so you don't necessarily need to worry about the offset to that token, as well as it also works in 32-bit and 64-bit environments, so you don't have to have different raw assembly strings. So just two different approaches. The C version is probably going to be a little bit better. And finally, we want to talk about exploit reliability with the remaining time that we have. So why do we want reliability? Because nobody wants a BSOD. Like on a local privilege escalation, you're shooting yourself in the foot, and that's just not good. Nobody wants that. Because if you're doing it on the remote exploit, I guess some people might want a denial of service. Maybe, not really sure. But so the sources of instability, I came down to 3 primary sources. Number one is going to be like corrupted structures. If you're overwriting stuff and it's just not going to work, and you're going to trigger some type of like an access violation. Token reference count, and then finally, where do you go after your code has executed? So sort of returning control back into the kernel. So we're going to talk about these 3 sources and sort of how to address them. This is definitely the section where the solutions that I'm trying to propose are not going to work in all situations. They're probably not even going to work in half the situations. It's very highly dependent, but this is just personal experience, and so I wanted to share what I have found. So corrupted structures. There is a region of memory that is shared between user processes and kernel processes that some objects and some information can be discerned from. This region of memory is marked as read-only, so that way the user process cannot modify those values, because if it did, that would introduce a huge vulnerability, and privilege escalation would be relatively trivial. But we can use this to be able to back up structures if we know that they're going to be corrupted at a later point in time. And the reason why Windows does map this shared region is strictly for efficiency. If all the memory needed to be in the kernel and be protected by the kernel, then anytime the user process wanted to have some type of a value, they wanted to be able to read it, they would have to make a system call that would have to have a context change into kernel mode, and that's very, very slow. So the kernel maps this page over as read-only, so strictly for efficiency reasons, so the process can run much faster by being able to access this information without having to make a system call. But so how do we address it? Basically, we back it up. We take that read-only information and we write it out to a pointer, and then if our exploit is successful, then we have code execution within the context of the kernel, and from that context, that page, or because it's not going to be at the same address, but it'll be at an offset, and we can know where that's at, but we can then restore that information back because we're running as the kernel. So the primary problem that you still might run into with this is that if you corrupt the structures and you don't get code execution, you're not going to be able to restore the data from backup, so you're still kind of going to be SOL. So that's something you kind of need to watch out for. And then the NT-HAL dispatch table, like I mentioned, that is a very reliable one that people can exploit by just writing over that pointer. By being able to restore that pointer back, people can do that as well, so that if for some reason some process is going to execute NT query interval profile, they're not executing where the shellcode used to be, which is going to be an invalid address. So basically just restoring that information back. It can be a little bit difficult when trying to restore information if that information is being stored in the kernel, because you can't necessarily just strictly read from it. So at that point, you need some kind of a read primitive. Once again, you would use a read primitive to be able to read out the data of the structure that you're about to corrupt. And once again, so that way you can still back it up. Writing it is always going to be easier if your exploit is successful, because you'll have code execution within the kernel, so you can just write all that back anyways. Pretty much nothing's going to prevent you. All right, so token reference count. This is a very old problem that has occurred. So when a token is stolen and it's just strictly copied over, the value, or the pointer rather, is replaced in the process structure, that token has a reference count. And what happens is every time that the process exits, that reference count is decremented. And when it gets to 0, that structure is going to be free because it is no longer being referenced by anything. It's not being used. So this introduces a problem where if you're exploiting a vulnerability repeatedly, over and over and over again, and the process that has been elevated dies or is exiting out gracefully or ungracefully, Windows is going to decrement that reference count, and eventually it's going to get to 0 and might prematurely free that token. And then when that token is referenced another time, you're going to have a blue screen condition because it's not going to be able to read out that information. So what are some solutions to that? We could go with clearing out the ACL of another process that completely removes the need to do any type of token stealing, anything like that. We could do that. But if the process you're injecting into, like WinLogin or something else that's super critical, if that dies, you're still going to run into the same problem. So it might not be the best. You could actually duplicate the token. You could either implement the reference count or call a function that will actually properly duplicate the token. That is possible. It's not practical from raw shellcode, though. Like we had mentioned in our raw shellcode, or we have two different types of shellcode that's implemented in C or assembly. It's not really practical from raw shellcode. You could technically do it, but I haven't actually seen anybody do it. This is sort of one of those things that people theoretically talk about. What I have seen, though, that is very practical and can be done from raw shellcode is a process in which people will, prior to elevating their process, prior to stealing the token, they'll back up the initial value someplace that will sort of persist for a little bit as long as that process is alive. They'll steal the token, do their business, and they'll return. And when that execution gets switched back to the user after they've elevated their process, that user can add a user, spawn a new system-level interpreter session, or anything like that. And then prior to exiting out of the process, they'll then restore that token. So this is practical from doing from raw shellcode. There are a few of those Ruby exploits that are implemented that do utilize this method. This does require that the shellcode can be changed and that the exploit can be reliably, or the shellcode rather, can be reliably triggered twice. And like I mentioned, when we have one of those write while where conditions and we overwrite the NT-HAL dispatch table, we don't need to trigger the exploit a second time. We can just replace our original shellcode, call NT-query interval profile again, and that shellcode is going to get executed a second time, and we can clean up after ourselves by de-elevating ourselves back down by restoring the initial token. So that way, anything that was done while it was elevated, Windows will take care of properly duplicating the token and everything, and so as long as it's restored prior to exiting, the reference count will be impacted because it'll be the original value. All right, so finally, we talk about returning control. So sometimes we've had exploits that in the case of after they have executed their shellcode and they have done their bidding, they served their purpose well, they still die. They still exit out, and when they exit out, they're, of course, returning back to the kernel. And sometimes we've corrupted things so bad that when it returns back to the kernel and it tries to continue execution, it's just going to fail. And we have a blue screen from that point. So what can we do? We can actually unwind the stack and return to an arbitrary location up the stack. And the reason why we can unwind it is because Microsoft uses a standard calling convention. So we can actually pull back the base address and we can work our way up the stack. And so the point is what we're just left to is where do we want to return. If you know for a fact from messing around with the vulnerability that if you return 4 or 5 frames up, that'll be okay. You could do that. But also because we all know that the kernel addresses are very trivial to differentiate between a userland address, we can actually have our code dynamically determine out where the where the last call to from user land was and where the first call to the kernel land was. And we can sort of find that and return to the frame just before that. And the reason why we would want it to be dynamic is, once again, because of these patch levels. These patch levels might introduce additional functions that might do a check or something like that. So what might work from your 4 frames up might not work on every version of Windows. But what you can do is you can walk up and find that last frame in userland by looking at the address, and instead of continuing to that, go up to the frame right before it. And the reason why you want to do that is because that is most likely going to be KI system service post call. And this is a function that, or this is code that is within the kernel that restores the context back to the userland. You cannot directly return back to userland because you're still going to be executing within the same context, and you'll run into all sorts of problems, so it's just not going to work. However, if you return back to that frame just before that, it should return everything back for you. So this is going to be very well suited for events where you have a system call that is actually triggering the vulnerability. Once again, like NT device IO control file is going to be very suitable for like this type of workaround. You can also modify and select the value that this system call will return. So a lot of people might be tempted to have it return a success code. I would recommend against that, though, because if you did use this technique because you were running into problems, then if you return a success code, the system is probably going to try to continue to do what it was trying to do ahead of time, so you'll probably just delay the error. You'll run into errors later on down the line. However, if you return an error code, it's probably going to hopefully stop what it's doing. This is all going to be very dependent on the code of like where it is actually within the call stack and like the code path to get to that point. It's of course going to depend on all the decisions that are made ahead of it, but if you return an error, generally it should know that something was wrong and that you can't operate on that object for whatever reason it was. So in this case right here, we have this stack that I want to point out. So all these addresses up here on the top are of course going to be all the kernel addresses, and they all start with BA, and then I have that red box. And that address that is on the top is that NTKI system service post call, which is the first address in kernel land, and very, very easy to determine because it is of a higher address than that one that is right below it, which is the NTKI fast system call return, so where it's coming from. So we want to return to that last one before coming back into userland, because that one will switch the context for us. So this is shellcode, so this that's very, very blurry. But it comes out into being about 29 bytes. This is in 32-bit, so we can actually use the register. So we would want to execute this after we've done our purpose, after we have elevated our process. So after that shellcode has been executed, we would want to run this. It's 29 bytes. That doesn't matter though, because we're in a local privilege escalation vulnerability. We can allocate as much space as we want, but thought I wanted to point it out there because I'm not really much of a shellcoder, but I got down 29 bytes, so that's awesome. And basically, it just walks up the stack by unwinding it, and it checks all the addresses against like 0x80, 000000, and so it's going to be able to determine whether the addresses are into a userland frame or a kernel frame beyond that, and it just returns, once it's found that, returns to the one just above it. So I kind of wanted to close out with mentioning a little bit about 64-bit exploitation. Really excited to see 64-bit exploitation that's sort of been picking up this year. In earlier 2015, we've seen more and more exploits coming out. The first 64-bit Windows kernel exploit that was in Metasploit was actually MS-1458, which came out, like I said, about late third or early fourth quarter last year. But we're starting to see this pick up. I think there's one that's about to be landed this weekend. But what people are starting to do is they're starting to realize that they can write their exploit once in C and then work it so that it compiles for both targets, which is very nice. Something else that's very useful for people that want to look into and are going to be reversing things on a 64-bit system is that on 64-bit Windows there is one calling convention. Only one. Always this one calling convention. 32-bit, you have things like cdecl, standard call, fast call, this call. While almost all the time Windows is going to use their standard calling convention, that's not necessarily the case. But on 64-bit, you don't really have to worry about that. It's always going to be the 64-bit calling convention. I also want to point out, WoW64 really complicates things. I have not seen any kernel exploits that are meant to run within a WoW64 environment There's a lot of things like pointer truncation. You can't really resolve the addresses. It's very difficult. I've read papers about them being developed for like pwn to own, but I've never actually seen them practically being released that is suitable for like a pen tester. So not quite there. So from a Metasploit perspective, if you are in a WoW 64-bit process and you do have one of those 64-bit exploits, it's basically going to tell you you need to either spawn a 64-bit process or you need to migrate into a 64-bit process. So you need to be on the native one. You're just going to be a lot better from there. And then finally, check for pointer truncation. Not when you're in a WoW 64-bit environment, but when you're in a native 64-bit environment, check for pointer truncation. It might be there, it might not be. It might be the difference between the exploit working on 64-bit but not working on 32 if the pointer is truncated, if any type of value gets truncated from some type of return. So closing thoughts. Kernel exploitation is flexible. Because you do have that execution ahead of time, you can sort of massage and manipulate the environment, set it up in the way that you actually do need it. And size doesn't matter. So you can have a giant exploit that's in like a giant DLL, and it's not like remote exploits where you are very limited in your attack surface. You have to, specially craft your like one TCP frame or whatever. It's not like that at all. So it's really much more open to how the attacker can manipulate the environment. And then my personal hypothesis and opinion, kernel exploit is going to stick around for a while. I hesitate to say that it's going to pick up. Just because exploitation is getting harder. That's the nature of the beast. Somebody somewhere is doing something right. But because we have seen the shift to client-side attacks, the need for kernel exploits is going to remain there, so that way we can sort of use that as the second phase of the attack to elevate ourselves. And with that, I'd like to open it up to questions. I have cool prizes. All right, nobody even wants prizes. All right. Further reading, I have lots of further reading. There's some fantastic research out there, and I really wanted to emphasize that a lot of this stuff, I tried to put footnotes in it. If you actually look closely at the slide, I tried to make references to it. A lot of it came from not only that page, but there is a second page. There's some fantastic work out there, and I really want to thank all these people for making this available to us. And with that, I'd like to say thank you for your time. I will be speaking, if you enjoyed this, I will be speaking again at 4 p.m. downstairs with Mr. Brandan Geis, and we're going to be talking about phishing. So if you want to look at that social engineering aspect and how you might be able to get somebody to give you user land access, that talk will be there. So thanks, everyone.